Hi, folks. Good afternoon. If you can hear me, just give me a feedback here. That'd be awesome. Yay, somebody says what?
I can hear you,
Oh, awesome. Beautiful. So,
but I'm the other moderator.
okay, awesome. So you can watch over it, right? That's great. So, hi, folks. My name is Paresh Motivala, and I'm from Boston. And today we must thank our sponsors, Swiss, Susi, and Quest Software. I'm also happy to say that Quest is also sponsoring the Boston BI SQL Saturday that is coming up on 30th March. So let me go ahead and say the PASS Summit 2019 registrations are now open. Actually, it's a significantly reduced rate right now, so you might want to go ahead and register just about now, okay? Because then the prices start going up like crazy. So if this ever moves by itself, okay, yes, it did. If you are interested in any shape or form, submit your uh, interest using this link at the bottom, surveymonkey.com. Right? This will also be uploaded for you to be able to go ahead and do this. Okay. The first PASS Marathon Spanish edition will take place on February 21. That is 1 week after the Valentine's Day. So please do not forget to register there if you are from that part of the world and can understand that language. SQL Server and Azure Data Services free event near you is a lot of them happening now. It's amazing. Even Microsoft has now started doing this during weekdays, and it's called the Azure Data Fest. It's being held in a lot of communities, but definitely this is something you want to learn new and polish up your or raise your game in the professional careers. Upcoming SQL Saturdays, my name is not here, which is sad, but Winnipeg in US, Canada, Port de Nome in Europe, APAC, it's Wellington, and Latham is Guatemala and Costa Rica. So without much ado, let's see, there are 30 virtual groups, out of which I'm sure something will kind of get your interest going. So please do, like I run the professional development virtual group. I just finished one session about 45 minutes back, and the database administration is the other one that I run. So, and you can connect with us and follow us on social media like this. So Facebook and Janice Griffin has 25 years of DBA experience. I think you would have started at what, SQL 6.0, Janice?
Yeah, I actually started with Oracle version 3, if you will. So.
Damn. Okay. So yeah, I wouldn't bore you with reading all this, but yes, before coming to Quest, Janice has many DBA positions working with both real-time networking, routing databases, and OLTP business-to-business applications. She speaks and has spoken at many SQL Saturdays as a database performance evangelist and mentored many DBAs and developers on best practices and database performance tuning. So I would definitely now hand it over to Janice. Janice, it's all yours, and I will make you the presenter just about now. Make presenter, and you are on your way, my friend.
Okay. Thanks, Paresh. Thanks for the introduction. I too want to welcome everyone joining me here today. I wrote this presentation because with Microsoft releasing so many releases of SQL Server here lately, and actually they've done a lot of things around indexes that are relatively new. Basically, I hear a lot of feedback. I'm not sure, Paresh, are you on mute?
I wasn't, now I am.
Okay, thank you. Anyway, I just thought it'd be great to do an overview on indexes. So let's get started. Let's see, where can I go? There we go. As Paresh gave my introduction, I don't have to go through that, but here's the agenda we're going to walk through today. Now, this is going to take probably all the time, so I would encourage you to, if you have questions, to put them in the chat window. I will try to get to them at the end. If I run out of time, I'm sure we have a mechanism in order to answer the questions and post them somewhere. I'll get with the organizers and see if we can do that. So please ask your questions. But as I said, this is, I'm going to go through a lot of indexes, Rowstore indexes versus Columnstore indexes. I'm going to talk about clustered indexes versus non-clustered. We'll see how they work with heaps. We're actually even going to get to memory optimized tables and indexes on those, and talk about hash indexes, and then finally maintenance and statistics. So it's a well-packed presentation. Like I said, hopefully you can download my slides. I'm going to be going through it pretty fast. But what is an index? It can be an optional object associated with a table or view. It can be one or more columns on a table. It can be unique or non-unique. Unique keys help enforce data integrity by keeping duplicates out of our data. It can speed up data retrieval, and really the main reason is to reduce I/O, both at the memory and disk level, because the less you read, that's the most expensive component is disk on a computer. So, and then once you read it into memory, it takes a lot of CPU actually traversing that memory. So if you can reduce that I/O, basically you've sped up the query. SQL Server has both on-disk and in-memory index types. They can be clustered, non-clustered, filtered or covering, Rowstore, Columnstore, hash, or memory optimized, non-clustered. And I'm going to go through each one of these. What's beyond the scope of this presentation is XML, spatial, and full indexes. I won't get a chance to talk about those. So let's get started. What Rowstore indexes are the traditional relational indexes that have always been there. Basically, they're B-tree structure stored on disk, and they can have 0 to many levels in their in an index, and they call that index depth. So, for example, this view here that I'm looking at, I have an index depth of 3, and I've got a root level, an intermediate level, and then the final leaf level. Now you can have many intermediate levels. It depends on how the cardinality of your index, how many unique values, and so on and so forth. So, but basically you can have 0 a level too, as well as if it's just fits one page, you're going to have 1 level. So it's basically the most efficient way to get to data quickly. And the reason why is because you can see here, if this were a clustered index, basically what happens is the data sits in the leaf level. If it's a non-clustered index that's sitting on a clustered, that's pointing to a clustered index, actually it'll hold a cluster key here in the leaf level. And then finally, if it's a heap, it'll hold the row ID, or a RID as people often call it. But that's just an 8-byte row ID of file ID, page ID, and slot number, so it can go to the data. So anyway, if I were to read on a clustered index, maybe look for a row number 5 in my index, I would go to root. I'd find 0 to 19. I'd go to that intermediate level of 0 to 8, find that, and then I'd go to the leaf level and find it here. So in a clustered index, I might only have to do 3 IOs, because basically the data is right there. A clustered index, as I said, you've got the root, the intermediate, and then the leaf data. Clustered index is basically the table data is ordered and stored by the clustered key. It can only have 1 clustered key because the data can only be sorted in 1 order. And then it can be used to quickly retrieve data if the query contains the left leading column of the clustered index. If you have a multi-column index and you don't include that left leading column, it will do, it'll read the clustered index, of course, because that's where the data is, but it'll do a scan, which is no better. It might be a little bit better because the table is ordered than a full table scan. It is used, and then also, the clustered index, if the non-index is on a clustered index, it actually holds the clustered key. So you have to consider that when you're actually creating your cluster index. What is that clustered key? Preferably, best practice is you either want a unique or primary key that rarely changes. Clustered indexes can become fragmented quite quickly if you're changing the primary key, because the data has to move as the primary key changes and has to move. So, or as the clustered key does. It should be small and narrow in size, because you have to remember, if you've got a lot of non-clustered indexes on the same table, basically what will happen is that cluster key is stored in each one of those non-clustered indexes. Good examples of clustered key I've got listed here. Identity columns are good. They're not usually intelligent. People don't really change them. They're just there for the cluster. But also you might not be very good, because you might sort the data consistently some way, and that would be a good cluster key if it happens to be small values. Or a composite key. Maybe you've got date and integer, and you're always looking by date. That might be a good cluster key. You can also use this new sequential ID function, which basically generates a sequential GUID, which will fill the data pages and the index pages completely. However, I don't like to use that. It's just such an ugly big key to me, and it's kind of non-friendly, if you will. Rowstore indexes, you've got a heap. And what a heap is, a table that doesn't have a clustered index. It's just not sorted in any order. So if you think about it, if you've just got data here, and as it randomly gets inserted, you might be in any page in this table. And so therefore, it's going to cause you more I/O. Heaps are not used a whole lot in SQL Server, just because they're very inefficient. The only thing you can do with a heap table is do a full table scan. And oftentimes that full table scan is all over the place, because, like I said, the data isn't sorted. Also, you can add a non-clustered index to a heap, and I've got an example of that we'll show. And then finally, you can have a non-clustered index. And these are all Rowstore indexes still, but the non-clustered index just holds, it's a separate object in the database. It only holds the index columns of the key, and usually they're the filtering predicates or the join columns in your query that you want to get to the data quickly with. Like I said, if the table has a clustered index, the non-clustered index will contain the clustered key. SQL Server will put it there implicitly for you. You don't have to add the clustered key. Otherwise, if it's a heap, then it contains the RID. More on non-clusters, it's usually much smaller than a table. So, non-clustered indexes are smaller in size, less I/O to get them in memory. They use less memory, and they give faster retrieval for a few rows. It actually, as you can see here, here's my non-clustered. If it's going to a heap, it's going to the data. If it's going to a clustered a clustered table or index, it's going to the leaf of the actual index itself to get the data. So actually, very efficient way to use and grab data that, especially if you're getting a small amount of data from a very large table. There's one thing about non-clustered indexes, though, that you should be aware of. SQL Server does implicitly add that cluster key to non-clustered indexes, but some of the tools don't show that is part of the key. Like show plan, for instance, you don't see, if you look at the COV, my sales order detail, I'm doing unit price index. It looks like only unit price is indexed. But unbeknownst to doing this SP help index, it's actually a covering index, and it's actually included the cluster key as well. So you have to use third party or look at space used to see if that cluster key is taking up space. And here I like the SQL Skills. They have written their own help index, and you download it. It's just a stored procedure, install it, and it actually gives you a nice view. So my covering index here says unit price, is the index key, but here's my included columns. And oh, by the way, these are the columns in the tree and the columns in the leaf. So it's kind of a neat visual to see that. Okay, the heap index, the heap example, and here's how it performs. We're going to go through a bunch of slides of the different indexes and how they work. We're going to go through a heap example. Now, basically, all I did was I took sales order detail and I did a select into, and I just called it a heap table. Now, what really I wish I had done is randomly put data in here as opposed to taking from a clustered table or a clustered index where the data was ordered, and then probably just put it ordered in my heap table, which is not necessarily true with a heap table. It's unordered data. But as you can see, you can see after I ran this, I ran a query. I'm just doing a select star from heap table. I'm just looking for a specific order ID. And I always set statistics IO on and time on because I like to see the logical reads and actually the CPU time and the elapsed time. So as you can see here, here's my execution plan. It did an index seek, but it had to actually go do a RID lookup because I did actually put a non-clustered key on it. It wouldn't have been very interesting to do not put an index on it because it would have just been a full table scan. Like I said, SQL Server, you don't use heaps all that often. The only time you would mainly use them is when they're for tiny tables or temp tables where, adding indexes and sorting the data to get it into a clustered index is not useful. You never use a heap for rows that need to be sorted or if ranges of data are needed in the query. So here I decided to, compare this to a clustered index examples. And you can see here, the index seek is still doing an index seek, 192 rows affected, same rows, same elapsed times, but look at the reads, only 9 reads as opposed to 195 for the heap, because that data was, all over the place. Excuse me. Now, more on the clustered index, if I were to not put that left leading column in my query and just reference the second column, it turns it into an index scan instead of an index seek. And so here I'm just looking for a specific sales order detail ID. It returns 1 row, but look at my time, 1.5 seconds elapsed. And look at my logical read, 64,145. So it did a lot of reading for that for that simple query. Now, I could fix this in one of 2 ways. I could change the code, add the order ID, or as SQL Server is suggesting, I add a non-clustered index on sales order ID. So I add that, and now you can see the difference. It's now doing still 1 row, but instead of the 1.5 seconds, it's now underneath a half a second. And it's only done 6 logical IOs as opposed to 64,000. You still have the key lookup here because of the non-clustered key. So other types of indexes you can consider is adding in, is a covered index, filtered index, or combination. And I'm going to run through those, plus have examples of them. But adding indexes is not always the right thing to do. You have to consider your insert, update, and delete activities or merging activities, anything that manipulates that data. Because when you add an index, you're adding a different object to the database that now has to be maintained and taken care of. So it'll hurt performance on inserts, updates, and deletes, or it may slow it down. So you've got to kind of have some trade-offs when you're thinking about adding index. Where do you need your performance? Is it inserts, updates, and deletes, or is the lookups more important for you? So also, they take up storage, so they come at a cost, and they can hurt performance, especially if you've got stale or missing statistics, or if the index is too wide or not selective enough. It just confuses the optimizer, and it may not use it or may try to use it when it really shouldn't. But you can add a covering index, and this can reduce IO significantly by actually including all the columns in the query in the include. Therefore, it doesn't have to go back to the table and do an extra IDO. So as you can see here, this is you create a non-clustered index, give it a name, and then you give it the index key, but then you include all the extra columns that are in your select clause. This is useful because it keeps the index very narrow, so the navigation becomes very efficient. It doesn't have to go through lots and lots of data in memory to find, certain rows. And then at the end, all it does is read the leaf for the data. So it's a great way to speed up performance too. I'm going to have examples of that as well as a filtering index. Now the filtering index basically gets a subset of the table. So it saves on storage, it saves on maintenance, and you just include the where clause, what you would have in your query. And it would only, like for this example, online order flag equals 1, basically this table will only, or the index will only hold where online order flag is 1. So it will be much smaller. Or you can have a combination where I'm not only covering it, but I'm actually filtering it as well. So let's add a covering index to my query. Now, my query was stupid, really. I did a select star, and I did that on purpose because I want to remind everyone, please don't ever code select star. It's a waste of storage, or a waste of IO, and a waste of memory, because it's going to bring everything in. If you don't need it, you're just thrashing memory for no reason. But since I selected star, in order to add a covering index, I have to add every column in my table. So this is what I would never do this in real life, but just to show you, it does improve performance by adding that, because I'm reducing my IOs. For the non-clustered index, I was doing 6, now I'm doing 3. Same one with the physical, and actually my milliseconds went down from 273 to 49 milliseconds. So, but like I said, the select star, a lot of third-party SQL code generators will do that, it's a lazy way to code, and like I said, it just wastes resource. Okay, one thing to say about covering indexes, they're not, this one wouldn't be very good at all because it can hurt performance for bulk inserts on very large tables, and lots of DML going on. I mean, I'm updating all of the index here as well as the table. So very wide covering indexes typically aren't very useful. Okay, here's a better example, and this is a true query from AdventureWorks, where I'm looking for certain products, probably to fill inventory, and I'm looking for popular products, and so I'm selecting custom ID, the quantity, the color, and I'm looking for names of last name like C, product name of mountain %42, color of black, and product ID greater than 900, just to give it some meat. And I'm joining sales order header to customer and customer ID, person to business entity, a person to business to customer on person ID, and then sales order detail to order header on order ID, and then finally product to order detail. And as you can see here, it did quite a few logical reads. It did 19,513 in an order header, 64,145 in order detail. My time was kind of sluggish at 2.2 seconds elapsed, and a little over a half a second on CPU. As you can see here, it's doing an expensive cluster index scan. And of course, the SQL Server is saying it's missing an index. And you can see high cost of 74. Look at the amount of data that it's returning by the size of this arrow. Well, let's that covering index. And when we do, we see several things happen. We see the costs go up in the sales order header. It's doing a clustered index seek, but it went up to 86%. But the index seek on that covering index basically went way down, and we're only doing 19 reads instead of 64,000 in some. So, and not only that, our 2.2 seconds went down to less than a half of a second. So that actually tuned it. Now we could be done there, but I wonder why this is so high all of a sudden, and we're still reading 19,000 records. So let's go try adding a covering index to sales order header. And I was, returning a few more rows from that. So I got order ID, order date, customer ID, and subtotal, because that was in the query. And I added it, and it used it, but the timing didn't change, 423 milliseconds, and it read less rows, but not very many, about 200, no, not even 200, 100 less. So is it worth it to add that index? I would say no. It didn't change the timing. I'm not even reducing that much I/O to maintain an additional index on the table. It's not worth it. So here's just some timing results. You can see the two tables I was working with. Sales order detail was about 4 million. Order header was 2 million in size. I always like to know the sizes of things when I'm starting to tune a query. And as you can see here, my timings went way down with the covering index, not so much with the covering index on sales order header. Well, what about a filtered index? We did have that online flag equals 1 in it. So it works on selective filtering predicates. So filtering index are very good for a small subset of a huge table. So it can improve performance and plan quality, because filtering and statistics are more accurate than full table statistics. And also it can reduce index maintenance and storage costs, because of course the index is going to be smaller, so the data of the table, and then it doesn't have to maintain the index unless the filter is changed, and that's the only time it has to maintain it. Ideal columns for filtered index are categories containing small values such as status, a flag, or a bit. Columns with distinct ranges of values, say department ID or warehouse ID. And then finally, columns that have mostly null values, like ship date. If you're always looking for where null, and then when they finally ship it, they put a date, maybe you should make it a filtering. And so that would reduce the subset of data that would have to go look through. You can't use filtered indexes when the queries return computed columns, or if they're complex predicate expressions in the query, like with the like operator, or lots of ands and ors. So it'll just the optimizer can't use it. Review, and also there's a lot of settings that you have to set correctly to have a filtered index. So I've got a link here. If you download my slides, it's quite a nice tutorial for filtered indexes, but you can see that I've got all the set commands here. There's quite a few of them. ANSI null has to be on. A lot of these are on. There's numeric round abort off. So you have to set all of those in order to create a non-clustered filtered index. So there's my filtered index again, and you can see when I go update that, and you can have applications that actually set these to something different, you're going to get an error on those applications that do that. So I created that filtered index thinking that the optimizer would use it, and I went and created it, but it ignored it. In fact, it just stayed with the cluster index seek, which had me scratching my head until I looked at the data, the actual data in sales order header, and you can see that there's data skew. For online flag equals 1, over about 90% of the table came back. That's not a selective filter. Remember, I said you want very selective filters for a filtering index, and that's not. Conversely, if I had it to equal 0, that's about 10%, a little more than 10% of the data. That might be a good filter if that was my query. So what about a filtered and covering index example? Make it like this index. So I decided to add this to non-clustered index, and I'm doing it on online order flag, and I add all the fields that I need in my query, and where online order flag equals 1. And it uses it, but the cost didn't come down. And look at the reads. The reads are no better than my covering index was. And so the timings didn't change either. So, it's not worth it. It's not worth it to maintain those type of indexes if you're not going to get a big bang for your buck. So what if we were to take that filtered index and change it a little bit and make my query be 0? Because I was telling you how selective that was. Look what it does when I change it to 0, because that was 12% of the table. It does use it. It changed it, and the cost is only 8%. And notice my logical reads. Instead of 19,000, I have 938. So, it still performed kind of sluggishly, though, at 58 milliseconds, but it did use the index and did reduce the I/O. Finally, the last thing about Rowstore indexes, they do take up stories. So data compression not only helps reduce the size of your database and doesn't, reduces the storage, but it can improve performance of I/O intensive workloads. Data is stored in fewer pages, so it's not reading so much into memory. Compression is not available in all editions, though. It only became available in 2016 SP1. But there's two types of compression. You can have row compression, which basically dedupes and takes out spaces. It does a bunch of things. It takes variable numerics and makes them fixed and space used. Page compression is a little more sophisticated in that it not only does row compression, but it also does prefix compression and dictionary compression. I wouldn't recommend that if you're updating and inserting into your data, because the recommendation is use page compression if the update percentage is low, and yet the scan rate is high. So that's the only time I do page compression. The trade-off on compression is, it does take up CPU resources to compress and decompress the data. So if you're CPU bound, you may want to, watch it quite closely if you're considering compression. There's more trade-offs or more definition of the trade-offs here in this link. Examples of a filtering covering index with the compression equals row is you just create your index, but at the end you say with data compression equals row. So here's the sizes. As you can see, my filtered and covering index basically was 4.8 meg. And I just went and got all the sizes for the indexes here, looking at DB partition stats, indexes, objects, and schemas. You can actually run this stored procedure SP estimate data compression savings and give it the schema, the object, and I don't bother. I just get it for the whole database, and you can or for the whole table, I'm sorry, and just say that, and I tell it to give me row compression, and it'll actually tell you the current compression and the requested compression. So this is uncompressed, in other words, and this is what it would do if I did row. So instead of that 4.8 meg, it would get it down to 4,032K. I mean 432K. Okay, so that was Rowstore indexes. They're stored row-wise. They're the typical indexes that have been there forever. But what came out new, I think in 2014, was Columnstore indexes. And basically, these are stored column-wise instead of row-wise. And they're great for analytical queries. They're, like I said, they're columnar in structure. They have what they call as column groups, and our column segments, and these column segments basically are related in a row. So it's in my sales order detail example, I've got 4 columns, and each column is sitting in a row group, and each row group can have 1 million column segments. So there you see an example of how it's stored. You can have clustered column store indexes, and if you do have a clustered column store indexes, the data is stored in the leaf. There is no key in key level in a column store clustered in or a clustered column store index. You can also have non-clustered column store indexes, which are great for row store tables. Think about a highly transactional system like you're taking sales, over the phone. But yet you have your marketing department or maybe finance wanting to look at that and forecast and do a lot of analytical queries on those. In the past, we used to have to break those out and put them in a data warehouse because it couldn't function and keep performance up for the highly transactional queries. With Columnstore, the SQL Server is smart enough to know when it's an analytic query and use it if it's in a column store. So it really speeds it up. Like I said, row stores, row groups, basically they're groups of rows. There can be 1 million of them in a row group, and they compress in a column store format. And then the columns segments are also compressed, so it gives you very tight data that's sitting in memory and on disk. Up to 10 times query performance, Microsoft says, and the reason why is because it uses vector-based processing, meaning that in one CPU instruction, it can go over many columns and read much data, so it's very fast. That alone, just by the vector-based processing, can increase it by 2 to 4 times. And then the high level of data compression is worth it too. It's a smaller in-memory footprint, up to 7 to 10 times better. And it's great, like I said, for queries that only get a few columns. They're doing a lot of group bys, maybe aggregations or summaries of stuff. Also, if you have a star schema with large fact tables, a clustered column store is marvelous, and I've got examples of those that we'll see. And then real-time analytics, like I said before, if you have a transactional system, but you've got other departments wanting to get at that data for doing some analysis, Columnstore might save you from having to set up a whole other area for them. So here is an example of the non-clustered column store index on that sales order detail, and I just put it on sales order ID, order detail ID, product ID, quantity ID, and you can see the significant savings, almost 5 times the savings versus the CIX is my covering index versus my column store index, and you can see almost 5 times the savings there in space. Okay, so here's how it performs. Now I'm just showing you the Rowstore index again. And so here I'm creating my covering index. And this is a query, a little analytic query I wrote where I'm getting first name, last name from those same tables with the same where clause. The only thing I'm doing is I'm getting total amount and total quantity. And you can see here it's using my covering index. And it pretty efficient. It did 38,623 reads out of sales order detail and only 35 reads out of sales order detail, so 355 milliseconds. Here's an example of adding my column store index, and you can see I can't have an include on a column store. I have to include just all the columns. So here's the creation statement. I create that, and I'll run my query. And you can see it's got a little new icon here for column store index, and it's doing a scan. And we go up here and we see there's no logical reads, no physical reads. I thought this was an error at first until I looked to the right further, because column store indexes are stored in lobs after they are compressed. So you have to look at the lob logical reads and the lob physical reads. But you can see all I did was change a covering to a column store, and I cut it down by 200 from 355 milliseconds to 263. Finally, I thought, well, if that really sped it up, maybe I'll just add a covering index or column store index on the order table. But alas, what the column that I had chosen was a computed column, and you can't put column store indexes on a computed column. Here's just some other queries that I did just for other timings. And a similar query where now I'm just getting the total quantity, and I tried to add that, and you can see covering was almost 3 seconds. We're just putting it in a non-clustered column store, cut it down to half of a second, really less than half of a second. So pretty good that way. Now, a clustered column store index, and like I said, they're great for if you have a star schema with a large fact table. And I've used this Department of Transportation site to get sets of data. And really, this site actually holds all the flights in the U.S. for every year. I don't know how many years it goes back. I downloaded a while back, 2015, and so this is my little star schema. And you can see my fact table on time, and then you can see the lookup table: city, market ID, weekdays, unique carriers, and airport. And so to create the table, I decided to create a clustered table, which you can see my creation here. And I've got my clustered key as the primary key. And then you can see how I've created my heap table. Now I'm going to walk through this on the next slide a little bit better. The easiest way to create a clustered column store is basically first create a heap, select into the heap, and so I did that from my on-time cluster table, and then you just create the column cluster index, and then what it'll do is it'll re-put that data inside the clustered column store. Indexes have no feed key fields. Like I said, it's all stored in the leaf block level. And how you create is you just create cluster stored column store index, and I called it on time CCI on my on time heap table. And then I added, you have to have a unique key on a clustered column store, so I added a unique non-clustered index, and you can see that listed there. So then I wrote this query, and I thought it'd be interesting to take this data and find what are the most popular flights, carriers and cities in the United States for year 2015. And it turns out it was Dallas and Los Angeles is spent the most time in the year, because I based it all around elapsed time and how much time in the air they were. And so you can see I'm selecting carrier name, originating airport and city, destination airport and city, and then I'm summing the total actual elapsed time to get total time, and I'm joining all my tables to my fact table there with their supporting keys. And so I run this, and you can see it's using my clustered index scan, and it actually took over 8 seconds. Really kind of sluggish. My on-time table, it read 28,887 logical reads. So then I just changed the query to point to my clustered column store. And when I did that, basically it increased performance by 5 times, down to 1,479 milliseconds, or 1.4 seconds, I should have said. And instead of those almost 9 seconds of the other. And again, you can see that it's used the clustered column store. Okay, there are restrictions with clustered column store. The restrictions, basically, they can't be in on a view. You can't use include, ascending, descending. You can't use alter index, although that's changed in 2016 and above. They are adding some alter commands to it. All the limitations here you can see in this link. Just wanted to show you the sizing compared to my clustered on time index that was 225 meg. This is about half. I had to include my unique key as well as the column store, but still it's about half the size. Now you can actually have indexes on memory optimized tables. These are good. Memory optimized tables are a great way to increase performance if you can use them. You can have non-clustered indexes. They're best for range scans or ordered scans. And when in doubt and you think you need an index, use this type of index. Columnstore indexes are great for analytical queries, as I said before, and you can have them on memory optimized tables. And then hash indexes, they only can be on memory optimized tables, and they're only good for equality seeks. That's what you use them for. It doesn't support range scans or ordered scans. You must include all the columns in the index, or the query does have to reference all the columns in the index, otherwise it won't use it. And then the data returned can't be sorted. There's more about hash indexes with this link there. So here's just creating my on-time table in memory to see how it performs. I didn't put any indexes on it yet, but I just created it. And I said, give it a PK, non-clustered, and memory optimized on, and then give it a durability clause. And I just chose schema and data. So that's how you get it in memory. But before you get it in memory, you have to actually create a memory optimized file group. So I first had to alter data, add file group, and you can see contains memory optimized data. And then, of course, you have to add files to it. So again, I run this query, and you can see it's more efficient than my clustered index scan, and it's not 8 seconds, but it's actually took more time than my Columnstore index, because that was like 1.4. This is 2.5 seconds. So let's try a clustered Columnstore index on a Mem-Optimized table. And so how you do that is basically you just say on mem and put it in there. And then I altered this, and you can do this in 2016 and above, and said add this index, clustered Columnstore. And so it actually did that. And you can see it actually had 9 times better performance than my clustered index, 888 milliseconds. So that would be a way to go if you have fact table, in my opinion, because it's very efficient. Now here's just an example of a hash index on a memory optimized table. And again, I'm showing you the clustered index first, or just the table scan, I guess, on memory, which was 704 milliseconds. It's a single row. I'm actually only looking up for a single row, I think. Now here's the hash index. And you have to add this clause, bucket count equals 100, I put 150,000. My table had a 1.5 million. And I don't know if that was a correct number of bucket counts. I didn't spend too long on it, but just to show you how it works, I thought it might be close. And look at the time, 16 times better performance, down 42 milliseconds to do that. So that's all the indexes and all the different considerations you might have to take when you're adding indexes or thinking about the different types of indexes. But also it's very important to do index maintenance. Indexes are objects in the database that need some care and feeding. And so it's very important to make sure they don't become fragmented over time, because if they do, that can slow performance. The optimizer may even decide not to use it. Also, if there's lots of DML activity, it may may fragment it more and actually quit, slow down the DML activity. And then actually to find index fragmentation, you can just run this query. And I just pass it the database. I don't pass it all of the values, so you can get quite specific there. But as you can see here, my fragmentation in this table, 50%, 25%. Microsoft recommends if it's between 5 and 30%, you should do an index reorganize, because that basically is much not quite as impactful as a rebuild. But if it's over 30%, you should rebuild it. And you can do that online now with using the online equals on clause. Unused indexes or little used indexes, that just takes up storage. You need to find and delete them because they slow down performance. And here's a neat query to do that. You can look at DB index usage stats, and that'll tell you how much they're used. You'd see the number of seeks, number of scans. My look and wage payment table, they haven't had any access to them, but those indexes are also primary keys, if I understand the naming there, so I may not want to drop them. But maybe the tables aren't even being used, I don't know. Missing indexes, again, you can look at these dynamic management views and functions to get some of this information, but remember this data is only good since your instance startup. If you restart your instance, this all starts over again. So if you, you may not catch them all, but you can reference these. And I use this function here. Basically, I select from DMDB missing index details. You can get the index handle here, and then you pass it to this function that basically gives you the columns that it needs, and they include columns as well. And then finally, you can see the operational stats, and and see how much inserts, updates, and deletes are happening, because they can slow down. Indexes can slow down performance because of those inserts and deletes. So as you can see here, I'm going to operational stats. I can see my leaf insert count versus my leaf update and my leaf delete, and then you can see the range scan and the singleton lookup. So how much are they used and how much are they updated? And then finally, your statistics. I think stale statistics, if you think about it, the quality of your execution plans are only going to be equal to the quality of your stats. If, SQL Server doesn't have the right information, it's not going to do the right thing. So this query here just goes against this index in tables and basically shows you your indexes and the number of rows changed and since the stats were last updated. So this one right here is probably not getting good information now from its stats because it's been updated over 98% since the last stats. So finally, in summary, indexes can speed up your performance, and that's why they're there. You can reduce disk I/O and memory footprint by using them. But it's important to know which ones to use. Know your index types. Rowstores are good for highly transactional systems. You've got the clustered index that holds the data, and you've got non-clustered index for key lookups. And then Columnstore indexes are good for analytical queries. Great for aggregating a few columns in very large tables. They can be clustered or non-clustered as well, and they can be on a regular table or on a memory optimized tables. And then consider hash lookups when you're doing single row lookups on memory optimized tables because it's very fast. And then finally, go review how you're taking care of those indexes. Index require a lot of maintenance. They require up-to-date statistics. So make sure everything's running right. And that's it. Thank you for joining me. I don't know if I've got a logo look and see if there's any questions.
Yes, I can actually field some of those questions for you. And
okay.
Yep, thank you. So one of them is, oh God, where did this go? Here you go. One sec. Say, where do we get the slide deck? You will get on the past DBA website. Somebody had asked a question actually. What happened? Let me see if I can pop out the question thing. Okay. Should we put an index on all foreign keys or only those foreign keys with high hits or high selectives?
Well, I think it's, if you're using, I didn't talk about constraints at all, but if you do have constraints, remember that constraint is there for integrity. And so if you've got a foreign key, in general, I would always index it because every insert, every update, everything you do, it has to go to look up, its parent to make sure it exists. And if it doesn't have a parent, then it'll give you an error because you can't insert the foreign key. If you don't index the foreign key, or if you don't do that, it's very hard to check it and traverse it. So it affects you in more than just your speed. It actually, I mean, on your selecting the data, it actually interferes with background updates and deletes. So I guess that would be my take in it. I always index my foreign keys unless it's a very, very small table and never changed or whatever, then it's probably not worth it. But hope that
So,
answers.
Sarah, if you want to say yes or no, please let us know. There's one more thing. What sort of an index is a full text index?
What sort of an index is a full text index?
It's a full text index, right?
Yeah. Okay. Well, full text index is basically used for it's a more sophisticated index that can understand character data. So if you've got a lot of string data, documents, that type of thing that you're actually searching through, full text indexes are great for that because they can actually quickly search and you index the full text, the actual data.
Okay. Then this one is, I think, something that I can also possibly work with you on this. Uh, says I still have questions uh, about fragmentation with NAS storage, index fragmentation with NAS storage. So before you answer that, right, and the defragmentation, there's another one which is kind of corollary to the earlier question. It says that uh, if the index defragmenting, just what is it saying? Oh God, there is no separator here. Saying if it is busy, when can we do this? Should we set the fill factor to 100? Now, what has happened is that over the past month or so, we have been having a specific issue in Azure where we have premium storage, which I would presume now everybody has flash storage for their databases. If that is the case, is there really a point in rebuilding the indexes every night? So, three in one question, basically, trying to see if you can.
Um, yeah, I'm not sure what they're asking. If they want, if they've got fragmented indexes,
Mhm.
um, I guess I'd have to ask, how they're rebuilding every night.
That is what, even frankly speaking, I used to do
Okay.
as a DBA. But now we had some heavyweight guy from Microsoft come and say, "Oh yeah, you guys are all screwed up. You don't need to do this every night. Now you can just, since you have flash storage, you can just do it once every week."
Oh, flash storage.
Yeah.
Um, yeah, I would say flash storage is it's actually in a cache, so it's probably not traversing um,
Disk.
the disk as much. So yeah, I wouldn't think you would have to, as long as you have it in flash, but and not as often. But I still would, at least do it. I don't know if I'd do it every night, but I think Microsoft is probably correct when saying that, because there is that buffer there that is the data is sitting in, so it isn't going back to disk and traversing the actual data all the time.
Yep. So then, few more, actually, quite a bit of engagement here by the customer. I mean, the patrons here is that how to resolve parameter sniffing issues or writing better queries. Is that the right answer, Janice?
Yeah, if you have parameter sniffing going on, maybe and you have data skew, then maybe what you should do is, not parameterize those queries. Because if your data is skewed, and depending, again, this all depends. I hate to say that's the answer, but it usually is.
Mhm.
But it depends on the makeup of the data. But if you've got, say, like my data skew, my example of 0 and 1 in that, and only two values, and I had data skew, but if I would have parameterized that, then maybe it would have used an index or wouldn't have used an index, depending on what it first sniffed. And that could be bad. So there are some reasons where you don't parameterize. You can't just say you always parameterize everything, never pass a literal, but it really comes down to data skew. Now, in the later versions in 2017, they have actually changed the optimizer so that it can adapt the plans. And it can adapt the plans on the fly, and adapt of one of three ways. But basically, it can do nested loops or hash joins. And the thing about data skew and a sensitive parameter sensitive data is it won't adapt those. It'll let all the plans run because of the because of the data skew. So some of that might not be as bad in the later versions as it is in some of the earlier versions.
Okay.
Hope that answers.
And this one is, I think, what SQL Server version is the filtered index available in. I think it's been available for at least 2014 upwards.
What was it? What was it? What index? What type of it?
So filtered indexes, right? They are available since what version?
I'm sorry, what type of index?
Filtered indexes.
Oh, filtering indexes.
2012, at least I know that
Yeah,
is.
I think they've been around since, I want to say 2012, but I'm not sure on that. I'm not 100% correct on that.
Okay, and this one is another depends kind of answer by Sakib. Oh, he just left. He had
Yeah.
mentioned how many maximum number of indexes a table should have. My answer is depends. Right?
Yeah, I mean, there's a philosophy. There used to be a philosophy going around that you should index every column of your table, and then it's just taken care of.
Mm.
But that is, there might be some instances doing that, especially if it's a, you never change table. Maybe it's a date table. If you think of a business date table where you have maybe all the business days in the year, all the holidays in the year, all the, you're going about it with different dates.
Mm.
That might make sense, but that table is never going to change. Once it's created, it probably will never change. So then that might be a case where you would index every column, but I would never. The more indexes you add, the more maintenance you have, and not only that, you give the optimizer too many decisions to make. I mean, when it's building the execution plan, it has to consider all of those data access paths. And depending on the number of indexes, and really, do you need all those indexes, or can you combine some of them to cover more queries? That's the way I would look at it. And you're right, Paresh. It does depend, on your situation. But like I said earlier, adding indexes isn't always the right thing to do.
Oh,
It can
yeah.
actually, it could actually confuse the matter.
Cool. But I think that's little over the time, but I think people stuck around.
Oh,
Thank
great.
you. Some awesome insights to this. This is also a good refresher for me. As I told you, I just lost my job yesterday. So
Oh,
uh,
great.
I learned a lot out of this. So it would be like one prep step for me for my next interview, possibly. You never
Yeah,
know.
there you go. Great. Well,
Thank you,
I
everyone.
want to thank you for having me on today. And
Anytime, my friend. Plan on coming to Boston sometimes. I know it's not close by, but next time.
yeah, it would be great. It would be
Yeah.
great to go out to Boston. I love Boston, but that's a
And I
nice
heard
area.
you guys just about 2 hours back, you acquired Joe Flacco as your quarterback now. So if you ever come back to Boston, yeah, we'll cream them. So
Okay. Yeah.
cool. Thanks. Okay,
Yeah.
guys.
Okay. Thank
Okay,
you.
folks. Have an awesome evening and happy Valentine's Day in advance to everyone. Thank you.